Right, welcome back. Now, by making use of the property of the translation generator, the first derivative in the exponential, we were able to simplify the expression of the propagator and bring all the derivative terms to the right and all the non-derivative terms to the left. This was a very important simplification that we could achieve because of this particular property, and then we had these important relations that in the limit that n tends to infinity, which we ultimately have to take, in the limit n tends to infinity, each of these yj's is normally distributed with a mean of 0 and a variance of d each of these yj's, and by using the central limit theorem we find that the summation of these yj's up to n are normally distributed with a mean of 0 and a variance of n d. So, that is where we concluded the last last class. Let us continue from there. Now, we define a Brownian motion. How do we define it? As you recall, Brownian motion is a sum of random variables, and each of those random variables are normally the random variables are such that the Brownian motion becomes a sum of those random variables, and at any particular point in time the aggregate of all those the sequence of those random variables is normally distributed due to the central limit theorem as a mean of 0 and a variance equal to the length of evolution. So, we define a Brownian motion by Wk is equal to minus root t by n. Remember that we talked about the step size of under root t by n, that is precisely what is happening here. So, Wk is equal to minus under root t by n summation of yj with j equal to 1 to k. Please note the subscripts, the indices. We have Wk is a summation of random variables y1, y2, y3 from 1 to k. Let us look at the properties of this Brownian motion to ensure that it is a Brownian motion. We have the expectation value of Wk is clearly 0 because the expectation value of each yj is 0. The expectation value of Wk square. Now, that is interesting. Recall that the expectation value of each yj is equal to d. Therefore, when you are multiplying by under root you are scaling the variable by under root t by n, the variance gets scaled by t by n. So, the variance will be equal to t by n, and since there are n yj's here, so we have t by n k into d. To reiterate, to repeat, each yj has a variance of d, there are k of them. So, the total variance becomes, and each of them are independent of the other. So, the total variance becomes k d, and we are scaling each y by under root t by n. So, the variance gets scaled by t by n. So, we have t by n into k into d, and dw, the increment Wk minus 1 is nothing but under root t by n yk, and clearly the expectation of dw is 0 because the expectation of yk is 0, and the expectation of dw square is equal to t by n into this expression, this particular expression, expectation of yk square. Remember, the expectation of yk square was d, therefore, it becomes t by n into d, and that is nothing but the d into the step size, that is d dt. So, let us now what do we have? We started with this first expression for delta, we simplified it by translation generator property, and we got all the derivatives to the right, we got all the other terms to the left, and then we introduced the concept of Brownian motion. By introducing the concept of Brownian motion to represent the sum of the yj's, we simplify the summation, the terms within the summation, and we write them as Brownian motions. It is quite straightforward. We write summation of yk as wk, and we write summation of y j plus 1 from j equal to k to n as a difference of two Brownian motions from j equal to 1 to n and then from j equal to 1 to k. So, j equal to 1 to n minus j equal to 1 to k. In other words, it is equal to y n minus y k, but there is a minus sign here in defining the Brownian motion, and therefore, it becomes y k minus y n. So, this is the operator form of the propagator. Why operator form? Because it contains the derivative operator to the extreme right. Now, we move on to find the expression for the kernel. The kernel has to satisfy this equation which is given at the top in the green box. Psi of x t is equal to integral d theta kernel x t subject to 0 theta psi theta comma 0. In other words, it transforms the state theta 0 to the state psi theta 0 to the state psi x t. It transforms the state psi theta 0 to the state psi x t. Recall that the propagator transformed the state psi theta 0 to the state psi theta t. Here we have the kernel doing a slightly different job. It is transforming the state psi theta 0 to the state psi theta x t. Now, as I mentioned, the propagator did the job of transforming the state x 0 to the state x t or the state at x 0 to the state at x t. This is transforming the state at theta 0 to the state at x t. How to work it out? Let us start with the continue with the expression for the propagator, and let us operate that on psi x 0. We get this expression with the d by dx operating on psi x 0. We make a simplification. Now again we use this translation property of exponential del by del x exponential, the second term exponential minus w n del by del x operating on psi x 0 does a translation in spatial coordinates, and it gives you psi x minus w n comma 0. This because it is a derivative with respect to the spatial coordinate, it does a translation with respect to the spatial coordinates, and it shifts psi from x 0 to psi at x minus w n comma 0. 0 is the time coordinate. So, it does not affect the time coordinate, it does not, because there is no time coordinate involved in the derivative. So, it only the spatial coordinate is there, and the spatial derivative operates on the spatial coordinates, and it gives you psi of x minus w n comma 0. So, this expression gives me the expression in this blue box due to the translation generation property of the exponential of the derivative. Now, what I do is I set theta equal to x minus w n. To simplify further, recall I have to bring this in the form theta comma 0 psi theta comma 0. So, what I do is I substitute theta equal to x minus w n. When I substitute x minus w n as theta, to introduce this constraint into this expression, I use a Dirac delta function. I introduce this Dirac delta function within the integration, and I write the integration together with delta x minus w n minus theta. That is precisely x minus w n minus theta is precisely representing this particular change in coordinates. We are shifting x minus w n, or we are changing x minus w n as theta, substituting x minus w n as theta, and in order to implement that substitution, I introduce a delta function x minus w n minus theta. So, that this integral operates now only over the expressions where this theta equal to x minus w n holds. The rest is simplified. X minus Wn is written as theta. So, it becomes u theta plus Wn, and now psi which was written as psi x minus Wn comma 0 now becomes psi theta comma 0, and we have the expression for the kernel, and the kernel is now can be written or is in the form of this expression, the last red box that we have, k of x t theta is equal to limit n tending to infinity, this whole expression together with this delta function, including this delta function. And that is clearly seen by comparing these two equations and comparing the expression for the k in this expression and this integrand. Now, one more step of simplification can be achieved. This is the relative expressions for the propagator and the kernel. The upper expression within the red box is that for the propagator that we had earlier, and the lower expression is for the kernel. Important thing is that in the propagator we have this first derivative, the translation generator, and in the second the kernel, that translation generator is replaced by the delta function. Now, we do a little bit more of simplification. What we do is we define a Brownian motion, again we define a Brownian motion by the expression that the Brownian path starts at y at t equal to 0. Therefore, W of 0 is equal to y. We define a Brownian motion that way. W 0 is equal to y. It starts at the path. The Brownian path starts at y. So, we have W 0 equal to y at s equal to 0. S is now the new time coordinate representing the time coordinate. So, at s equal to 0, we have W 0 equal to y, and at s equal to t, that is the conclusion of the path, the terminal point of the path, we have W of t, small t, that is W of small t is equal to y plus W n, that is at s equal to t. That represents, and at any intermediate path we can represent for any intermediate value of s, what do we have? We have W s is equal to y plus W k, where how do we define k, or what is the relation between k and s? S is equal to k under root t upon n. K is, recall, k is the number of steps, right, time steps, and each step is of length t by n. So, in terms of continuous time, it works out to k into t upon n, which is the arbitrary or the general value of s lying between 0 and small t. Making these substitutions, I can write the summation as an integral. Now, assuming that this W that we have defined now is continuous Brownian motion, I can make this substitution, replace the summation by the integral u of W s integrated within the limit 0 to t. So, this gives, and the rest is quite simple. The delta function now operates because it is W n minus y, x minus W n minus y, it becomes x minus W t. Recall, what is W t? W t is equal to y plus W n. So, substituting y plus W n is equal to W t, we get this expression, the delta function, and the rest is mere substitution. So, we are now able to write the expression for the kernel in terms of a continuous Brownian motion, an integral of a function of a Brownian motion, rather than a summation of a discrete sum of random variables. So, now the important thing, what have we got? We have got the kernel as the expectation value of a certain quantity, expectation value of the exponential of an integral. Now, when we have the expectation value obviously it will be integrated, it will involve a probability density function because or a probability mass function either way, and then it has to be summed over or integrated over as the case may be with respect to this expression of random variables. So, the basic point that I want to emphasize is that here we are having to talking about the continuous case, we have having a probability density function, and then we are having this random variable here. We are integrating the expression in order to arrive at the expected value, and we have to do this integration over the various possible realizations of this random variable, and because this random variable is continuous, there is an integration here. What do we find? It is an integration over all possible paths, and therefore, it is called a path integral. Right. So, we have arrived at this expression. Recall, this is the origin of this path integral can be traced back to the diffusion equation. Therefore, this represents an explicit solution of the diffusion equation. Now, some definitions before we proceed further. The concept of autocorrelation functions. As I mentioned several times, a stochastic process involves a sequence of random variables. Random variable at t equal to 1, random variable representing the process at t equal to 2, random variable representing the process at t equal to 3, and so on, a sequence of random variable which is usually indexed with respect to time. Now, the correlation between these random variables at different points in time conveys very important information about the dynamics of the process, about the memory of the process, and therefore, it is a very important parameter as far as various stochastic processes are concerned. It is defined as the correlation function. Precisely, we have the expectation, the correlation function is defined as the expectation of x at t 1 and x at t 2. The expectation of this value, you see, you will have various realizations of t 1, x at t 1, and you will have various realizations of x at t 2, work out the correlation between them, and that is precisely what gives you an indication of how the process is moving forward in time. And this is as you can see on the right hand side, this represents the summation. In the case of discrete processes, it represents the summation over j and k of all possible realizations of the stochastic process at t equal to 1, at t equal to 2, together with the joint probability, together with the 2 time joint probability of the process being in state j at time t 1 and the process being in state k at time t 2. That is what is called the correlation function. Now, this probability point issue can be simplified further, and we by using Bayes theorem we can express it at a 2 time conditional probability and a 1 time probability. For a stationary process, it gets simplified further because time translation does not change the properties of the system. Therefore, we can write T x E of x t 1 x t 2 as equal to E of x 0 x t, and the rest of the properties also get simplified. The conditional probability also gets simplified. It becomes and then this probability, the 1 time probability also gets simplified. You can use the probability at t equal to 0 for that matter, and from t equal to 0 you can have the conditional probability that this system moves to the state k at time t, and work out the conditional work out the correlation function, autocorrelation function, and that way with respect to t equal to 0 you can work out the autocorrelation function at any other point in time. It would be representative of other autocorrelation functions also, provided the system is a stationary random process, a stationary stochastic process, that is time translation does not influence the system. Now, this is the case where the definition that I have given above is the situation when the mean value of the random process is is 0. If the mean value of the process is 0, then the above formula operate. If the mean value of the processes is not 0, then we measure correlations in respect of deviation from the mean. We define deviation from the mean as delta of x is equal to x minus the mean of x, and delta x is equal to x minus mean of x, that is the standard formula for deviations, and we work out the correlation as the expected value of delta x 0, delta x t, the correlation between these two, and the formula change slightly. This additional term in the green box comes into play. For Markov processes, the autocorrelation becomes all the more important. Recall, what are Markov processes? Markov processes are those processes where the process has limited memory, the memory is confined to the immediately preceding state. So, in the case of Markov processes, the autocorrelation function has special significance, because the autocorrelation function depends on the conditional probability, and the conditional probabilities determine all the joint probabilities in the case of Markov processes, and the joint probabilities are what we want ultimately, because our path probability is a sequence of joint probabilities. So, knowing the joint probabilities, we can calculate path probabilities, and joint probabilities are determined by conditional probabilities in the case of Markov processes. For continuous stochastic processes, these are the formula, slightly different from what we have for the discrete expression. Only basic difference is that we replace the summation by integration and the probability functions by probability density functions. The rest is more or less absolutely parallel. Right. Now, I have talked about the diffusion equation in a lot of detail. You would recall when I started with deriving the diffusion equation, what we did was we talked about the random motion of a particle in a fluid. We had certain predefined probabilities of the particle moving to the left, moving to the right in an infinitesimal time, and on that basis we arrived at the diffusion equation. We did not explicitly encounter the Newtonian force equation. We did not present the dynamics of the particle in the form of a Newtonian force equation and then try to solve it. We had a slightly obscure approach to the study of the dynamics. We studied the dynamics purely in the context of probabilities. We did not talk about the dynamics per se as a Newtonian framework, as a dynamical framework where the laws of motion manifest themselves explicitly. Recall, no, the Langevin equation it does just that. It gives you, or it presents the dynamics of the system which is subjected to some kind of a stochastic force field as explicitly presenting it in the Newtonian framework, and that is what I want to take up now. We are talking about the dynamics of the Brownian particle. Recall that a Brownian particle is a microscopic particle which is immersed in a fluid and which executes random motion due to the collisions that it encounters with the various molecules of the fluid. Let us assume for simplicity the mass is assumed to be unity. In any case, we can rescale other quantities if we so desire and make the mass unity. So, that is not an issue really, and that does not affect the generalization of the exposition. Now, we can write the assuming that the mass to be unity, the force equation, recall that we are working in non-relativistic dynamics in Newtonian dynamics. In Newtonian dynamics, we can write the equation of motion as the acceleration, that is the rate of change of velocity, is equal to minus gamma v is the velocity, plus L t. The terms I will explain in a minute, but this is what is the Newton's equation of motion for the Brownian particle, which is encountering collisions from various sides randomly by other particles of the fluid. Now, what is the property of the force that we are talking about in the current context? Number one, there will be one in this particular equation. In fact, we have introduced a damping term as well. The first term, this first term minus gamma v is a damping term, and it operates linearly in velocity, and in the absence of any force, it will cause the dissipation of energy and result in the absence of any LT, that is any external force, the particle will gradually come to rest due to the damping term. So, we have one damping term, which is gamma is a constant quantity, and it is linear in the velocity. And then we have a stochastic term, which is LT. Let us look at the properties of LT. LT is a random force, random in the sense that it's an impulse which takes place at random intervals of time. The force is the manifestation or of collisions between the various fluid molecules and the Brownian particle. So, let us explore the physical characteristics of this particular force before I talk about the statistical properties. Now, the first thing is that the time of collision is very small, as a result of which the collisions may be assumed to be instantaneous, and then the collisions from one particle due to one particle, the impact of the collision due to one particle and the impact of the collision due to another particle are mutually independent, they do not influence each other. And thirdly, the force with which they collide with each other, that force is not constant, that is also varies rapidly. Now, keeping in view these three properties, keeping in view the first property, collisions are spontaneous, collisions are uncorrelated with between each other, and the collision force varies rapidly. We are able to model it in together with a delta function, and that gives us the following two properties of the random force or the external force. Number one is, on the average LT will be equal to 0, and number two, the correlation or the autocorrelation of LT at different points in time is a delta function, or is a modified delta function, with gamma, capital gamma here representing the strength of the force, and LT dash is the autocorrelation, expected value of LT dash is the autocorrelation. So, the autocorrelation of the random force that is exerted on the Brownian particle due to collision between various molecules is in a sense delta correlated with an additional term that represents the magnitude of a scaling term. This is nothing but a scaling term which represents the magnitude of the force by which they are impacted. Right. Now, while talking about this, we have taken a certain approximation, and a very strong approximation. The approximation is that the time span in which the effect of the force acts on the impulse of the force acts on the Brownian particle due to the collision is very small. It is much smaller than other time scales that are relevant to this particular problem, and as a result of which not much approximation is introduced by the use of delta function to model this colliding force. Now, we have talked about average force being average of LT being 0 or the average of the external force being 0. We have talked about autocorrelation. So, there must be the issue of ensemble error. Now, when we talk about ensemble, the ensemble in this particular situation can consist of many particles at the same time, they which are observed and the properties assessed, many particles being observed and their properties determined in the same field, or a single particle may be tracked over a sustained period of time in such a way that or to such an extent or to such a length that the time span is large enough for the impact of one collision and not to impact the or not to influence the impact of the other collision. This is the fundamental condition that has to be met when we talk about the ensemble, on the basis of which the averages or the statistical properties that I have mentioned earlier, that is these two properties, property 1 and property 2. These two properties that I have mentioned, these two properties must be calculated very carefully with respect to ensembles which satisfy either of these two conditions. Either we have many particles in the same force field and they are assessed at the same point in time, or we have a single particle being tracked at different points in time, with the points in time being so far apart that the influence of one collision does not carry over to the other collision. And even in the first case, the particles that are studied together at the same time must be distant enough such that they do not get influenced by each other. The Langevin equation is a special case of the general stochastic differential equation. My next program is to take up a detailed solution of the Langevin equation, where again we will encounter the path integral, and then we will also establish a similarity between the Langevin equation, which represents the pure dynamics of the system, which represents which is explicitly showing you the Newtonian dynamics, the laws of motion governing the system, and the Fokker-Planck equation, which represents the probabilities of the conditional probabilities of various issues involved in the dynamics of the system. So, that is what I have in the agenda. Thank you.